Hello, my name is Sumit Sagar Hota. I'm a PMR, PhD scholar at IIT Palakkad, and today we'll discuss lecture 6 to lecture 10 by Professor Sagar Sir, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion. This is the week 2 of the live discussion section. Just we quickly go through the MCQs, and at the last I will solve some problems. So the first question is, eddy viscosity is a turbulent transfer of what?
Sir, I think option B, heat.
Okay. Yeah. If you know the answer, you can just type in that text box. Okay, and that's good. Correct. Okay.
Okay, sir.
Okay. So eddy viscosity is a turbulent transfer of momentum by eddies. Okay. So next one, which among the following is the uh, equation of Bernoulli? Okay. So basically, Bernoulli's equation is what? TdS equal to dH minus VdP. Okay, which is option A. So here you should note that it all are the specific quantities, like this is your specific entropy and this is your specific enthalpy. Okay, so we say, and this is your specific volume. This obviously you know temperature and pressure. This is the Bernoulli's equation. Okay. So for the isentropic flow, which of the following is the correct one? So basically for isentropic, as the name suggests, entropy equal to what? 0. So okay. So okay, just we tell directly from the name. If somebody asks you how you can prove it, so just apply the Bernoulli's equation. Okay, so if your entropy equal to 0, that means the change in entropy is also 0. Okay, so ds equal to 0, that means if for isentropic flow, what is the required equation? You get to know dH is equal to VdP. So this is the equation for the isentropic flow. Okay. So next one. Okay, so which among the following is Euler's equation? Okay, so Euler's equation is obviously a very simple equation which equal to v dv plus dh. Okay, just quickly we'll go through. So v dv plus dh equal to 0. Okay, these are all are specific quantities. Okay, this is a specific volume and this is a specific enthalpy. Okay, so how we know this is Euler's equation? Because here there is no heat transfer term, okay, in any kind of energy equation. So in an energy equation, if your adiabatic term is absent, then that equation is called Euler's equation. Okay, so that's a kind of also question can be asked. Identical to adiabatic form of energy equation. This is called your Euler's equation. Okay, so which of the following is the formula for momentum principle? Okay, that's very simple. Obviously the last one, P1A1 plus P2A2 plus the force term leads to mv2 into mv1. Basically I can directly prove you this thing. So we can take one control volume. So this is the control volume. So P2A2 mv2. Okay, so again P1A1 and this is your force term. Always mass term try to compress the system, and pressure and force are always in the one direction. So that's actually a trick to know. Okay, always pressure and force term is opposite to the mass into volume or the momentum term. Okay, so okay, so and this is your area A2 and this is your area A1. Okay, so now what is the area? Maybe A is equal to A dash by L and M is equal to M dash by L. Okay, this is your meter square, this is your kg and L in meter. Okay, so what we are doing, we will apply the conservation of momentum in the counterclockwise direction as positive or anti-clockwise direction. Then if you can see P1A1 and P2A2 try to rotate the system, and also F try to rotate the system anti-clockwise or the counterclockwise direction, but mv1 and mv2 try to rotate the direction in the clockwise direction. So obviously mv1 and mv2 terms going to be the negative and these other terms P1 A1 P2 A2 and F going to be the positive term. So directly write down P1 A1 plus P2 A2 plus F gives rise to mv2 into mv1. So this is the formula for your momentum principle. Okay, so we can go for the next one. So define the stagnation temperature. Obviously stagnation leads to a very simple term. Stagnation means velocity equal to 0. Okay, whatever it is, temperature, pressure, whatever. Stagnation, mostly the question will be asked stagnation velocity and stagnation temperature. Okay. Temperature at 0, velocity. Okay, so what is the viscosity of water at 30 degree Celsius? So these are some of the quantities you should remember, because in the exam they directly give the formulas and try to expect from you the answers. Okay, so some of the quantities you should remember, especially for water and air, at least can remember this quantities. Okay, so mu of H2O at 30 degrees Celsius is equal to 0.801, and what is the unit of dynamic viscosity? Pascal second or kg meter per second. Okay, so air also I write down. With air also we need 100 degrees Celsius equal to 1.872 into 10 to the power minus 5 kg meter per second or Pascal second. Okay, so yeah, the answer is B, obviously. So next one, the dash section of a nozzle or diffuser is called throat. Okay, so it's a very simple one. So I will do two types of two types of nozzles. Okay. So this person, and if you really know this thing, this is your throat. Okay, so basically this is a what? Minimum. This is the minimum section of a nozzle or a diffuser. Okay. Okay. So I just mentioned this is your convergent divergent nozzle. Okay, this is the nozzle with the flow is going this direction. Okay, and this is your diffuser, depending upon the flow. As the area will decrease, then it is the nozzle. If the area will increase, it will become the diffuser. Okay, so let's go to the next one. So in a adiabatic flow, what remains constant? Obviously it's the adiabatic name suggests, but the temperature obviously going to be constant. Okay, but you can see there is two options are there which are similar. You can see it. Enthalpy. So enthalpy, you know, always Cp delta T. So if the temperature is constant, that means dt tends to 0. That means your enthalpy is also going to be 0. That means your enthalpy is equal to also constant. Okay, so both stagnation enthalpy and stagnation temperature. In that question also, if the entropy is also there, entropy is also 0. But yes, it depends on the pressure or volume, because here pressure and volume nothing mentioned, so directly we are taking enthalpy. Okay, okay, so just quickly go to the next one. So when Mach number less than 1 and the flow area decreases, then what? Okay, so Mach number less than 1, so they are telling Mach number less than 1 and area will decrease. That means, okay, when the flow goes like this, then the area will decrease. So if the area will decrease, then what will increase? Obviously velocity will increase and pressure will decrease. So okay, so just we know from the continuity equation, a1 v1 is equal to a2 v2. So a is inversely proportional to your velocity. Similarly, p plus 1 by 2 rho v square plus rho gh is equal to constant, which is your Bernoulli's equation. Okay, so that means the pressure will also decrease and velocity will what? Increase. So obviously option C, both the things will work. Okay.
Hello, sir.
Yes.
Sir, is that stagnation pressure, sir? Or static pressure?
Here actually stagnation, you see stagnation means the velocity will be 0. Okay, so here there is no concept of actually stagnation unless and until it's mentioned. Here pressure will decrease, but we don't know, it may go, it can go to the 0. If it will going to the 0, that means the area will be so small, that means the flow means, and the velocity will be so high, that means velocity may go to infinite, then only the pressure will come to 0. Okay, and obviously practical scenario velocity cannot go to the your infinite. So yeah, in more or less it's very high and very low, and obviously it's obviously not possible to achieve a 0 pressure. Okay, so stagnation, most probably stagnation options will be there, that will be a wrong option. Okay, stagnation or static, all these options. Okay, decrease or increase will be the correct option. Okay,
What if they given a stagnation pressure, sir? What we have to choose, sir?
then
They
you
given.
go, that stagnation will be the wrong one. Okay, don't choose the stagnation pressure. Okay, that will be the wrong option then. Okay, that option you don't choose. Okay, rather decrease, increase, or less high, something like that if they want to give, because you see in the question it's written area decreases. Okay, so like that options obviously going to be the case. Directly stagnation, all these things obviously they won't ask. If they will tell that okay, the velocity is going to a very high velocity in such a way that there is a chances of it tends to infinite or something like that, in those cases you may choose the option of stagnation, pressure, all these conditions. Okay, so that's what the idea. Okay, let's go to the next one. So this is also similar one. Okay, so there we see the nozzle, here it's the what, diffuser. Okay, so here you see in the same conditions again, the Mach number less than 1 and the area instead of decreasing it's now increasing. Okay, so now obviously this is a kind of what, diffuser. Okay, so similarly if the area will increase, the velocity will what, decrease, and pressure will increase. Okay, so this is a kind of diffuser, you can tell. Okay. And here you can tell it's a nozzle. So obviously because you know very well A1 V1 is equal to A2 V2, and A obviously inversely proportional to the velocity, and same formula 1 by 2 rho. Okay, whatever, so that's the whole idea. So obviously, so that means what is going to decrease, velocity is decreasing and pressure is increasing, that means it's option C. Okay, so now for a subsonic flow, which among the following options going to be correct? So subsonic flow, a convergent passage becomes a diffuser. Okay, so basically if you see very well here in the what does the subsonic flow means? Subsonic flow means Mach number less than 1. Okay, and all these two cases I am now showing you the Mach number less than 1. Here if you see, nozzle becomes the nozzle only and diffuser becomes the diffuser only, so there is no interchange of things. So obviously, so B option, if you really see, divergent passage becomes the diffuser and the convergent passage becomes the nozzle. What exactly now we see in the previous two questions. So our options will be B. Okay, so the subsonic flow, okay, so subsonic
Sir, what
yes.
if the inlet is sonic, sir?
Can you repeat again?
What if the inlet of the
Actually your voice is not clear.
number is sonic?
Yes.
Am I audible, sir?
Yes.
What if the inlet Mach number is... What is if the inlet Mach number is 1?
Okay, so those cases obviously it's not neither a subsonic or nor a supersonic flow, but in some cases we are telling this Mach number less than or equal to. Okay, so means the same condition will apply for your that actually what I will write down, Mach no less than or equal to 1. Okay, mostly we are telling subsonic flow. Okay, so or we can mean sometimes this thing in the practical cases this thing actually measured. Okay, but when Mach number equal to 1, it's actually a sonic flow you tell. Okay, and for sonic flow same condition for subsonic will applied. Okay, so there is nothing change is there. Okay, So that's the reason in most of the cases they mention m less than or equal to 1 in place of m less than 1. Okay, so obviously in the question they have to, because it's a simple question that directly mentioned less than 1, but if they want to complicate it they can obviously write down less than or equal to, so that you will confuse. Okay, or you may choose the C option, both mentioned. So yeah, so it's a simple question, so that's simply they told. So yeah, for your m equal to 1, same subsonic conditions will be applied. Okay, so that's the idea. So let's go to the next one. So now obviously the condition is Mach number greater than 1. So now when Mach number greater than 1, the same formulas won't be applied. Okay, so because now the flow becomes compressible. That's the most important term I am now telling. Those from that term many questions can be asked. Okay, so for the compressible flow, the Bernoulli's equation cannot be applied, neither the continuity equations. Okay, so then which equation we can apply? Some of the equation which you will study in the gas dynamics will be applied, like dA by A is equal to dV by V into m square minus 1. Okay, so now if you see in the question it's written m greater than 1, that means this will be your greater than 0. Okay, and they are telling the area decreases. Okay, so that means this area decreases means this will be what? Negative. Okay, so now this one is negative. This whole term, if you really see, so m square is positive means obviously this whole term going to be greater than or equal to 0. But we are considering that m starting from 1 only we are considering, because it's only greater than 1, so that means it can be also greater than 1, and either not greater than 0, it will be greater than 1. That means this term is actually your positive term. Okay, and this is your negative term. Okay, so that means to make this left side equal to right side, we have to multiply with one negative side, then on sign, then only this will be positive. So that means our dV going to be what? Negative. Okay, so dV going to be negative means what? It is going to be decreases. Okay, so if the velocity will decrease, that means what? Pressure will always increase. This thing everywhere it's valid. Okay, so so though you can see the options, obviously option C will be the correct one. Okay, so your velocity going to decrease and pressure going to increase. Okay, so obviously you can write down also m square minus 1. So if m greater than 1 implies m square minus 1 greater than 0. Okay, that also one thing. Okay, or positive you can tell. Okay, so that's what the whole idea. So next question can go. So obviously yeah, same question, but here area will increase. So m is greater than 1. Just quickly I write down these things because everything going to be same. So dA by A is equal to dV by B into m square minus 1. So can you tell me here what's going on? You see, velocity is decreasing, and you know in which case the velocity will decrease, or in the nozzle or diffuser. So obviously we know very well, for diffuser only the velocity will what? Decrease. Okay, in the same way we can go to this question. So obviously here m is greater than 1, not if I don't write down. So for m greater than 1, that means m square minus 1 greater than 0. Okay, so if it is greater than 0 means this is your positive, this is your positive term. So now area, what area is increasing, that means this is your also positive. Okay, so both are already positive, so no need to worry. This is, you just multiply with positive also, so that the left and right will be same. So this is also going to be positive, which means velocity will increase, which leads to a decrease in pressure. Velocity increasing, which leads to a which type of device? So basically going to be a what? Nozzle. Okay, so yeah, so basically the same question, but now the answer will be different. For a supersonic flow, the convergent passage becomes diffuser, exactly, because we see here convergent passage becomes a diffuser. Okay, because velocity decreasing, convergent passage, and which means a diffuser in the supersonic flow, and a divergent passage becomes the nozzle, exactly, in the divergent passage, because area is increasing and velocity is also increasing, which leads to a nozzle. Okay, so that's what the idea. Answer will be A. Okay, this is your supersonic flow. Okay, so the next one, the bow occurs at what Mach number? Okay, so if you really know this term bow and bow shock waves, okay, so this will be very simple. This is a very if you know it, then only you can answer, otherwise you can't. Okay, so it's a very simple one. Bow always occurs at the what, very high Mach numbers, especially if you see the supersonic jets, there you can see these bow shock are occurring in these kinds of flow. Okay, so obviously it's applicable only for
Sir,
yes,
which shock is stronger, sir? Bow shock or oblique shock, sir?
oh, I actually don't know that what you see, bow shock is a kind of you see, both are
Detached
whatever you are
shock.
telling, I understand. But you see, there is three kinds of shock. We know also normal shock. Okay, then oblique shock. Oblique shock means what? It depends on the angle. Does not depends on that. It's not a kind of shock. Okay, it depends on the angle. But here it does not depends on the angle. If when the velocity is this, then this kind of shock we can see. Okay, so which one is stronger? If you can more particularly, we can't tell, means it depends on obviously the Mach number, in which Mach number it can operate. Okay, so we can tell this oblique shock or shock inclined with some, with respect to incoming air, then it is your oblique shock. But yeah, I don't know, but yeah, I will check the bow shock and all this thing. What I know, maybe both are depends on the what do you call Mach number. Okay, but the situation whatever you are telling is are different. Okay. Okay, most probably I will tell you what exactly this thing. Okay. Okay, so what is a bow shock exactly? If you really know, then only this your doubt will be clear. Okay, this bow shock is a curved shock wave. Okay, this is a curved shock wave. Okay, this is so higher oblique angle. Okay, then your oblique shock. Okay, okay, this can be seen in the what blunt bodies. Okay, okay, and what does this do? This decreases flow velocity from supersonic to subsonic. Okay, and obviously and causes what? Non isentropic thermodynamic transformation. Okay, so by writing, why I write down all these things? So obviously from all these points we are really going to see, so obviously the bow shock will be more powerful than your oblique shock. Okay, because it's having very high oblique angle than your oblique shock, and this is that much powerful that it will make a isentropic condition to a non-isentropic condition, which is very difficult for any kind of shock to do. Okay, and it can decrease the velocity from your supersonic to subsonic, even hypersonic to also subsonic or supersonic. So this is very powerful shock. Mostly in your fighter aircrafts we can we are making this mechanism for sudden stops or all these things. This bow shock can be formed. So if we really want to see some of the examples of bow shock, okay, so basically maybe bow shock obviously practical example are there. Practical example, if you can see this example, we can see also solar wind we can tell. Okay, from sun, if you can see one shock wave will means when there is a kind of increase in temperature, all this thing, then this solar wind will come, and when it touches the air surface, because air surface is obviously a kind of a blunt body, and because of that there will be a shock wave formation is there, and those kinds of shock wave formation are called bow shocks. Okay, and obviously not only Earth, any other planets we can see. This is a practical example, but this can be possible through different kinds of aircrafts also. Okay, this is their intentional doing for their advantage of high speed braking, all these kinds of cases, but this needs very high shock, means very high velocities, and and the shock wave is not exactly forming at the back of that blunt body. It's a detached shock, it's not exactly at the back, somewhat distance away this shock wave can be seen. Okay, So this whole thing, that's actually, I think I go a little more detail. Okay, so yeah, so more probably, yeah, it's a supersonic flow, so we can tell Mach number greater than 1. Okay, so more specifically, it's more very much greater than 1. Okay, so that's what the idea. Okay, so let's go to our next one. So 17th one. Okay, a boundary over which the physical conditions undergo changes is called what? Okay, basically it's a very simple one. A shock front. Okay, basically shock front happens due to what? Shock wave. Okay, so yeah, this is a shock front. Then next one, a shock wave caused by driver gas is called what? Okay, so basically this is called contact front. Okay, this is also the boundary layer between driver and driven gas. Okay, okay, so these are the contact front. Okay, so next one, when the fluid flow is discontinuous, what is established? Okay, so so fluid flow is discontinuous. Okay, so obviously it cannot form a heat or it cannot form a pressure. Obviously, if you see, because these are some of the physical quantities. Okay, so if you really know, directly you just choose control volume. If you don't know the answer, that also. Okay, so this is obviously a control volume. So when this flow is discontinuous, okay, there are chances of formation of obviously what, this control volume. And where this control volume can be formed, it's a form established around the shock wave. So what does this means discontinuous? Okay, this is a very what you call tricky term to tell discontinuous. Okay, fluid always continuous, there is no kind of discontinuity in the flow, but they are telling discontinuous means something else. Okay, but obviously we will see the continuum hypothesis everywhere. Okay, it's valid everywhere. Okay, so they are telling discontinuous means this discontinuity leads to something else, which leads to a entropy P2 increase. Okay, over a what? infinitely small. Similarly, infinite means very okay, bigger or very smaller. Okay, here it's bigger. Okay, so that means if the fluid becomes discontinuous, it leads to a increase in entropy for a very long larger region. Okay, so and in that larger region is called what? Control volume. Okay, and it forms around say what? Shock wave. Okay, so that's the idea. So we go to the next question. Okay, shock. Okay, obviously this is a very simple question because already I discussed everything about this shock wave. Okay, so obviously this is a oblique shock. Okay, so there's three kinds of shock you can see: the oblique shock, bow shock, and normal shock. And obviously the bow shock is the most powerful one. Okay, so this shock developed due to angle variation with respect to what? Flow. With respect to flow direction. Okay, okay, so this is already I tell everything. Okay, but one of the characteristics of bow shock is also if it is forming in a continuous pattern. Okay, it does not mean that it's the shock wave is there and at the in the shock wave it's obviously continuous wherever it's forming, and that position only it's continuous. It does not mean that everywhere it's continuous. Okay, so maybe if one blunt body is there, so here this wake regions and form, and this thing is actually the continuous one. If you really going to see. Okay, so actually this is a kind of bow shock. Okay, sorry, this is not a bow shock, but this is a, we can tell plus bow shock will start from here. We can tell this is a blunt body. Okay, not the bow shock. Okay, yeah, here the that is a bow shock. Okay, actually this is your blunt body. This is your wake region. Okay, and it is obviously a continuous one. Okay, this is actually formed continuously. It can be uniform or non-uniform, but this is a continuously it will form. Okay, this thing. Okay, depends on the type of flow. Okay, so actually the answer will be B. So yeah, obviously this is You know very well Boso will always for a Mach number greater than 1. Okay, so yeah. So 22 shock generated due to an interaction of two bodies are called what? Okay, so two bodies leads to what? Moving shock. Okay, the shock can move. Okay, so where it will move then? Okay, so moving shock, so interaction. So obviously moving shock is a, this will propagating into a low pressure region. Okay, so then moving shock. Okay, so this will propagating into a low pressure region. Okay, so if it will propagate to a high pressure region, then what will happen? High pressure region. Okay, so when it will propagate to the high pressure region, then it is called what? Expansion wave. And when it will propagate to the low pressure region, it's called shock wave. Okay, so these two things you should also remember. Okay, this can be asked as a question also. So let's go to next one. The shocks generated due to the trailing exothermic reaction is called what? Obviously exothermic means what? The temperature will increase. In all these three conditions, in which cases the temperature will increase? Obviously it's a detonation. Okay, we can see also, if you see when one fighter aircraft is going so fast, okay, there is one very huge reactions, huge sound came. Okay, so in the kinds of dry air kind of conditions, okay, so those reactions kinds of detonation you can also tell. Okay, okay, especially this mostly happen in those cases where what you called some combustible airs are there or something. That means less carbon dioxide, all this thing which will means helpful in this detonation process. So yeah, so or it's happening at very high velocity, mostly for hypersonic and maybe generation 5 aircrafts. The shocks generated due to trailing exothermic reaction. So when this will happen, when the wave traveling through a medium of highly combustible and chemically unstable medium. Okay, so this is the situation for which this detonation will happen. Okay. So yeah, now we go for the problems. In an aircraft flying at an altitude where the pressure was 35 kilopascal and temperature is minus 38 degrees Celsius, the stagnation pressure measure was 65.4 kilopascal. Then calculate the speed of the aircraft. Okay, it's a very simple question. First write down what are the things given. Pressure 35 kilopascal, temperature minus 38 degrees Celsius, convert it into Kelvin, always 235 Kelvin. So what is the stagnation pressure given? 5.4 kilopascal. Okay, then what is the sonic velocity or the velocity of the sound? Square root of gamma RT. So what is this value? 1.4. R for air 287, temperature in Kelvin 235 Kelvin. Take the square root, we will get a value as 307.28 meter per second. We know very well the gamma of air 1.4, R for air 287 joule per kg Kelvin. Okay, so this is the velocity you found. Now let's apply in the formula of what? Stagnation pressure. We know PS is equal to P into 1 plus gamma minus 1 by 2 into Mach number square to the power gamma by gamma minus 1. Okay, so substitute the value and get the answer. Okay, 35 1 plus 1.4 minus 1 divided by 2 m square 1.4 by 0.4. Solve it and get m as 0.988. Okay, and you know very well what is Mach number is the actual velocity by sonic velocity. So implies, so what is the actual velocity? Mach number into sonic velocity 0.988 into the velocity we found 307.28. Okay, so what is the actual velocity of the aircraft? 303.85 meter per second. Okay, so this is the velocity. So if we go to the next one, okay, the air is expanded reversibly and adiabatically in a nozzle from 13 bar and 150 degrees Celsius to a pressure of 6 bar. The inlet velocity of the nozzle is very small and the pressure occurs under the steady state flow condition. Then calculate the exit velocity of the nozzle. Okay, so this is a little lengthy, but yeah, we can do it. Okay, so yeah, what are the things given? You can see the pressure is your 13 bar and P2 will be your 6 bar. Okay, T1 150 degree Celsius plus 273 423 Kelvin, and your C1 equal to 0. Why? In the question, if you see, the inlet velocity of the nozzle is very small. Okay, so we are assuming it as 0. Okay, we have to find out the exit velocity. Okay, and okay, expanded means so this is expander or what, but you see it's a nozzle. Okay, just don't confuse. Okay, just so here it's written reversibly and adiabatically. What does it mean? It means W equal to 0 and Q is equal to 0. So adiabatic we have to represent like this, adiabatic. Okay, so that means your Q equal to 0 and W 0. That means, and here we are assuming Z1 is equal to Z2. Z2 is Z1 Z2 are the height. Okay, this height is actually we are assuming same. Okay, okay, so this we are assuming. This is for your reversible, this is for your adiabatic. Okay, so let's apply the energy equation at the point 1 and 2. So basically your Q is 0, W is also 0, and C1 is also 0. This is given. This is your adiabatic. This is reversible. Okay, so now if you just rearrange, you will get H1 is equal to H2 plus C2 square by 2, because already I told Z1 is equal to Z2, so these two will also get cancelled. Okay, so now what will be your C2? Your C2 is equal to twice of H1 minus H2 square root. Okay. So what is H1? Cp delta T. Okay, delta is equal to Cp delta T. So 2 Cp T1 minus T2 square root. Okay, so obviously we are assuming the flow as what? Isentropic. Most of the questions will assume this one, especially for the nozzle, and for that T2 by T1 equal to P2 by P1 whole to the power gamma minus 1 by gamma. So here 6 by 13, we can see it, 6 bar and 13 bar are given, they just substituted gamma 1.4 minus 1 divided by 1.4. okay, this value comes out to be 0.8013. okay, so you're going to find T2, 423 into 0.8013, which gives to a 339.16 Kelvin. okay, so now substitute in C2. So 2 into 1005 into what? 423 minus 339.16. So what is C2? 410.509 meter per second. So okay, this is the answer. So okay, let's go to the next one. okay, so the air enters a frictionless adiabatic converging nozzle at 10 bar 500 Kelvin with a negligible velocity. The nozzle discharges to a region of at 2 bar. If the exit area of the nozzle is 2.5 centimeter square, find the flow rate of air through the nozzle. Assume the air having a Cp 1005 joule per kg Kelvin and Cv 718 joule per kg Kelvin. Okay, so let's try down what are the things given. So obviously P1 10 bar, P2 2 bar, T1 500 Kelvin, A2 2.5 centimeter square is equal to 2.5 10 to the power minus 4 meter square, and C1 is equal to 0 because negligible velocity. Okay, here it's mentioned. Okay, and here I am assuming 1 as inlet and 2 as exit. Okay, so what is Cp given? 1005 joule per kg Kelvin, then Cv 718 joule per kg Kelvin. So we need to find flow rate of air. Okay, gamma I can assume 1.4. so let's go for solution. So we're assuming isentropic flow. So directly I write down T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So we are assuming 1 to 2 process, 1 to 2 in the nozzle as isentropic flow. Okay, so what is T2 is equal to 2 by 10, 0.4 by 1.4 into 500 Kelvin, which leads to T2 315.69 Kelvin. So now we have T2. Okay, so I will directly write down the energy equation because we already solved all this thing in the previous question. The energy equation for C10, Z1 is equal to Z2, Q equal to 0 and W is equal to 0. Q equal to 0 for adiabatic condition. There is no work done in the what? Nozzle. Okay, so for all these conditions, H1 is equal to H2 plus C2 square by 2 and C2 is equal to 2 into H1 minus H2, okay, which is to 2 Cp T1 minus T2. So 2 into 1005, 500 minus, okay. So now C2 is equal to 608.65 meter per second. We can really notice it's near to the Mach 2 velocity. Okay, at the exit. So what is the flow rate of air? A2C2 obviously. What is area? Okay, okay, so this is your answer. So let's go to the next one. Okay, so okay, helium gas at 5 bar and 75 degrees Celsius enters a convergent nozzle with negligible velocity and expands isentropically into a space at 3 bar. Then calculate the mass flow rate per square meter of exit area for helium and the Cp and the gamma values are given. Okay, 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 so let's directly go through it. So let's write down the critical condition. Okay, For critical condition, the Pt by P naught is equal to 2 by gamma plus 1 whole to the power gamma by gamma minus 1. Pt total pressure, P naught is the initial pressure. Okay, so P naught is equal to P1 also, okay, which is equal to 3 bar. And what is Pt? If you can see, okay, so Pt we can calculate from this formula directly. Okay, so substitute the values. 2 by 1.667 plus 1 to the power 1.667 by 0.667. This is 0.487. If you solve it, substitute, so 0.487 into 3, 1.4613 bar. Okay, so if you can see, really it's less than P2 because P2 is 3 bar. Okay, so that means if you know always if the total pressure is less than the exit pressure, then what, the nozzle will not be choked. Okay, this is very important condition, when the nozzle will choke. Okay, and what does it mean? The gas will expand. Okay. Okay, there is no choke condition here. Okay, so yeah, so let's apply that T2 by T1, P2 by P1, all this as isentropic conditions, isentropic flow conditions. So obviously T2 by P1, P2 by P1, gamma by minus 1 by gamma. Just find out T2 from here. T2 is equal to 348, 3 by 5, 0.667 by 1.667. Solve it, you will get T2 as 283.67 Kelvin. Okay, so we know R is equal to Cp minus Cv. Cp is given 5.19, Cv also given 3.11, so R comes out to be 2.08 kilojoule per kg Kelvin. So gamma also we can find out, sorry, gamma already we know, we can now find out Cv. So obviously it's from there actually I found out all these things, because gamma and Cp I think given in the question. Okay, in the question if you see it's given gamma and Cp, so if you become surprised how I found out the Cv, the procedure I am now showing. So, and we know gamma Cp by Cv, so Cv is equal to Cp by gamma, so Cp is your 5.19 by gamma 1.667, 3.11 kilojoule per kg Kelvin. Okay, whatever. So let's go to the next solutions. We have to calculate what? The density. Okay, so what is the density at the exit? So rho 2 is equal to P2 by RT. So P2 3 × 10⁵. So 2.08 × 3 into 283.67. Okay, so rho 2 gives to be 0.51 kg per meter cube. Okay, so again energy equation we can apply. For Q0 W0 Z1 equal to Z2 and C10. Okay, W0 nozzle, Q0 isentropic expansion, it's given in the question. Isentropy means reversible adiabatic, obviously, and C1 equal to 0 also given in the question. Okay, and for that we know H1 equal to H2 plus C2 square by 2. Okay, so C2 is equal to 2 into H2 minus H1 is equal to the square root of 2 Cp delta T. Sorry, this is H1 minus H2. So let's substitute then. So what is C2? C2 is equal to 2 into 5.90 into 348 minus 283.67. The C2 comes out to be 817.16 meter per second, which is more than Mach 2. So we need the mass flow rate per square meter at exit. So mass flow rate per square meter of exit implies m by a2 rho 2 v2 0.51 into 817.16. so here m by a2 comes out to be 416.75 kg per second meter square. Okay, this is the answer. Now let's go to a small question, then we'll end. Okay, so the air from a reservoir is to be passed through a supersonic nozzle so that the jet will have a Mach number of 2 if the static temperature of the jet is not to be less than 27 degrees Celsius. Then the minimum temperature of air in the reservoir should be what? Okay, so what are the things given? Obviously the Mach 2 T2 27 273 300 Kelvin. So gamma of air 1.4. okay, so we go for solution. T1 by T2 is equal to 1 plus gamma minus 1 by 2 into Mach number square. Okay. So T1 by 300 1 plus 0.4 by 2 Mach 2 square. Okay. Is equal to 1.8. So what is your T1? 540 Kelvin. Convert it into degree Celsius. 267 degree Celsius. Which is your option C. Okay. Okay, this is the last question. So thank you very much for attending the section. If you have any doubt, you can ask in my comment section of YouTube channel, and you can any question related to your lectures you can ask in NPTEL forum for the question and answer forum for NPTEL. Okay, so thank you very much for attending the section, and good night, and we'll meet the next week again 6 to 8. Okay, thank you.